welcome in everybody. In today's class, we are going to be discussing torque. And as you see, at the bottom of it, we've got the little Greek letter tau. It's another T. And just when you thought that, physics wasn't going to have a different type of T, we do. So now we're just adding to our collection of the variables that have T in it. So this one is the Greek letter tau, and this is what we get used for torque. And that torque equation is equation number 14. Now, the variable that gets used in the equation is that little t. The unit for it is N times M, and you'll see why that comes about later on. So just make sure that you understand the difference. And remember, as of right now, we have a couple of different t's. We have a lowercase t, which is time. We have an uppercase T, which stands for period. The unit for both of those are seconds. Just remember the difference between period and actual time. And now we are adding another T to it. This one's tau for torque. All right, so the definition of torque. Essentially the ability of a force to cause an object to rotate about an axis. In simpler terms, it's a force that causes rotation. Here's the key part. The force must act perpendicularly to the object in order to cause rotation. So if you think about it, when you're pushing on a door, you push perpendicular on the door to open it, and you're rotating it. That force is perpendicular to the door. And what is it actually perpendicular to? Well, it's the door hinges. So it rotates about the hinges, and you apply a force, and you are able to open the door. And if you think about it, if you're standing next to the door and it's kind of open, if you push parallel to it, meaning you push at the little thinner edge of the door, nothing's going to happen. If your force is, pushing towards the same direction as where the hinges are, you're not going to be moving the door. You're just pushing onto the door, and that force is going towards the hinges. But when you, like a normal individual, when you open the door by applying perpendicular force to the door, it causes it to rotate and to open. So make sure that the force is acting perpendicularly. All right, another definition, we're going to have what's called the fulcrum, and it's the point about which the object rotates. So there's different scenarios, different objects, and they all have a fulcrum. And that fulcrum is the point about which the object rotates. So as you look at these two pictures, kind of mentally think, or can you visually see where the fulcrum in both of these are? And the fulcrum is at those points right there. So if you think about the little wrench, it rotates about that point. And if you think about that seesaw, that's where it's balanced, and that's where it rotates from. So that's the fulcrum. But here's 4 different scenarios, and you have to decide, does it cause torque, meaning does the force in the situation cause a rotation about an axis? So scenario 1 is pushing a child on the back while he or she's on a swing. Scenario 2, a child's weight is acting downward on the face of a seesaw. Scenario 3, pulling down on a wrench as you try to unscrew a bolt. And finally, scenario number 4, wiping dust off the face of your TV screen with the palm of your hand. So those are your 4 scenarios. Think about the way the forces are acting. Think of how it's applied. Is it perpendicular or not? And think of it as, does it cause a rotation? Meaning, does it cause torque? All right, let's go ahead and see what the correct answers are and what the reasoning behind each one is. So scenario number 1, pushing a child on the back while he or she's on a swing. The force here is the push from your hand, and it acts perpendicular to the child's back. So yes, this does cause torque because the child rotates about the axis of the swing. So that was a perpendicular force to the child's back, and it causes a rotation with the axis of the swing. Scenario number 2, a child's weight is acting downward on the seat of a seesaw. Again, this force is the child's weight. it acts perpendicular to the seat of the seesaw, so it causes torque because the seesaw rotates about its fulcrum. Remember the little picture that we saw earlier with the fulcrum? So that's where it rotates about. Scenario number 3, pulling down on a wrench as you try to unscrew a bolt. So the force is the pull of your hand pulling downward against the wrench. It acts perpendicular to the wrench. And in this case, it's perpendicular, and it also causes torque because the wrench rotates about the bolt. So this was the wrench that we saw in the image next to the seesaw. And finally, number 4, we are wiping off dust with the face of your, or we're wiping off the dust, excuse me, we're wiping the dust off the face of your TV screen with the palm of your hand. So in this case, the force is your hand pushing dirt off the screen. Hopefully you've got some kind of fiber, so hopefully you've got some kind of towel or anything like that, not using your bare hand, but that force is acting parallel to the TV. This does not cause torque because you're not rotating TV, and it's not perpendicular to the surface. So that's parallel to the surface. So key takeaways: make sure that the force is perpendicular and that it is causing rotation. All right, so this is equation number 14, and this is what I kind of referred to earlier, where I said that there's going to be an F, but that's not the fulcrum in the equation. So the actual equation, equation number 14 in your formula sheets, is tau is equal to F, which is a force, times R. Now, this R can be called the lever arm or the moment arm, or sometimes even the torque arm. So now it's T is equal to F times R. As I said earlier, we have a couple of different T's, so make sure which one we're using here. This one's for torque. The unit for it is N times M, and as you look at the equation, it should make sense as of Y. The unit for force is newtons, so that's where that N comes from. The unit for R, any kind of distance, is meters. So that's where the unit for torque comes in. It's N times M. Again, the R is a perpendicular distance from the applied force to the axis of rotation. So, like I said, it can be called the lever arm or the moment arm, or sometimes even the torque arm. But it's the perpendicular distance from the applied force. Now, in previous classes and previous lessons, we've also seen R, and each one was a little different. When we talked about circular motion, the R was for radius. When we talked about gravitation, the R was the center-to-center distance. And again, we're using R. The key thing about all of these are that they're all a measure of a distance. It's just different type of distance, but the unit is in meters. So as you go about your circular motion and gravitational assessment, just be aware of the differences, and this is what I meant by this equation, and these problems will not be on there. So there's. All right, so let's go ahead and do a sample problem. A door hinge experiences 50 N times M when 35 newtons is applied to the door handle. How far away is the door handle from the hinge? Now, the reason I specifically wrote this problem like this without mentioning the words and the terminology of specifically torque or lever arm or force is because I want you guys to be in the habit of being able to identify what each number represents based on the units. Remember that you don't have to memorize the units. If you're in doubt, you can just look in through the formula sheet and see where you see those units and see what word is next to them. So again, no mention of force is made, no mention of torque is specifically made. We just have the units. So based on the units, you can figure out which one's which. So the 50 is our torque, and the 35 is our force. And the question is asking for how far away is the door handle from the hinge. So that's asking for a distance. Therefore, it is asking for R. So to solve it, it's just like any other problem that we do. Make sure you write your unknowns and knowns. R is unknown. Distance should be in meters. Tau is 50, and the force is 35. We have our equation. Tau, or torque, is equal to force times the lever arm, F times R. And we're going to go ahead and substitute our values with it. Our torque was a value of 50 and the force was 35. So it's 50 is equal to 35 R. And since you're isolating or solving for R, you divide by 35 on both sides. On the right-hand side, it cancels out. And 50 divided by 35 gives you 1.43 meters. So that's how far the door handle is and where you applied that force from the hinge. Okay, this is an important example for many different reasons. Now let's think about if you have a door near you, kind of take a look at it. There is a demonstration that you can do and kind of figure out how the distance affects things. So the reason why the door handle is always so much further away from the door hinge, and it's pretty much the furthest point possible, it's because it makes the job easier, meaning that you have to apply less force in order to give the same amount of torque. So if you are by a door, and usually I would demonstrate this myself in a classroom, if I try to open the door, anybody can open a door if it's propped open with just basically the smallest little force using one little finger, right? But that depends on where you apply that force. So where the door handle is and the furthest point away from the door hinge, if you apply the tiniest amount of force with one finger, you can open the door. If, however, you try to apply force with the same finger at the point where it's closest to the hinge, so the closer you are to the door hinges, think about just an inch away, you're not going to be able to open the door. Now, again, please don't try this, and please don't do it to the point that you injure yourself, but it makes it very difficult. So in order to be able to open the door from somewhere closer to the door hinge, you're going to have to apply a lot more force. So the same force that you applied at the furthest point away is not going to work. So this is why torque is important, and it relies on two things, force and the distance where we apply it. So if you think about certain things like wrenches and so on, if you're trying to change a tire, there's a reason why all those tools are so much longer. If you think about a golf club, there's a reason why it's so long. And imagine trying to play golf with a very tiny thing about the size of a toothpick. You're not going to be able to do much. So as you increase the distance, you can have a lot more or a lot less force in order to achieve the same thing. This also happens in exercising with gym equipment and machines. So, and it's also similar to the way where doing barbell versus dumbbells work. The barbell allows the force and the weight to be further away, whereas with a dumbbell, it's much closer. So that's why you may notice that, you can do a lot more, lift a lot more when it's with a barbell as opposed to when it's dumbbells. And if you've ever done any kind of exercise on machines, you'll notice that you could push a lot more weight, but that weight does not translate to you coming and doing the same thing in free form exercises. So there's a reason why, because there's always torque involved and the distance affects everything. Okay, which way will it twist? Now this is important. So you do have to realize which way something twists. So torque will either cause an object to twist clockwise or counterclockwise. And a counterclockwise twist gives us a positive torque. So I'm going to get into the example for that in a second. Clockwise twist gives us a negative torque. So here's the way I teach it. And I said the way I teach it because on the next slide, we'll see a different method. And I don't like that method for different reasons. And I will say why. So let's look at counterclockwise twist. If you're thinking about the handles on a clock, if it's going counterclockwise, it means going back in time. Well, we know in real life we can't go back in time, right? But think about a video game. So if you're turning back time in a video game, Or if you're picking up a time boost, it's almost as if you're basically going back in time. You can do that in a video game. So think about like, a little racing game or some challenge that you're doing and you pick up a time boost. Well, that's positive. So if it's going counterclockwise, going backwards in a video game, you're gaining back time. So in this case, I would say that's positive. So just remember that. That's, to me, a lot easier to remember. When you think about a clockwise twist, again, think about the handles on a clock. And if it's going the regular clockwise that it's supposed to in our regular normal life, then at that point, it's negative. And the reason for that is because time keeps on, clicking away and keeps on ticking away. So you're never getting that time back. So you're constantly losing time. It's like, as of right now, you're not going to get 5 seconds to go back. There's no way for us to go back. So if as the clock goes clockwise, the handles go clockwise, that's a negative torque because you're think of it as losing time. So that to me is a lot easier than the next method that some people try to teach, and it's called the right hand rule. I don't like this. I prefer not to teach it. This is up to you if you want to go ahead and try it out and read it. Part of the reason why I don't like it is because, for one, it only works with your right hand and it doesn't work with your left hand. So what if someone doesn't have right hand? And the other part is the whole thing of it is based on what feels natural and what doesn't feel natural. And, some human beings have different capabilities. And some human beings, could easily rotate their wrist in different ways and their joints far more than the average person. So all this is purely based on how it feels, and I'm not a fan of this. So, like I said, the way I've always remembered it is think of a clock handle, and if it's real life, time's taken away, you're just constantly losing time. You're never getting that back. And if that's the case, losing it means negative. And if you were able to turn back time, which you can't in real life, but you can in a video game, the only way that happens is, well, if you go back or, if you pick up a time boost. So that's the way that I remembered it, and that's the way I've taught it over the years. And I hope that this makes more sense. If, however, you want to go ahead and try this, by all means do so. But like I said, I have my reasons against it. All right, so let's get into it. Is torque a scalar or a vector quantity, and why? So remember, scalar is basically a number in a unit with really no significance of direction, whereas vector does have direction. So still you get the number unit. So torque is actually a vector, and it's because the two things that it relies on, the force and the distance of the lever arm, are both vectors. So torque is a vector quantity. Now, some questions that you may get are going to be going back to the same type of concept logical questions, and these are super easy for you to do as long as you follow the original versus the new methods that I've taught you previously. This works with anything. So what happens to torque if the distance of your lever or moment arm remains the same, but you increase the force? So again, when they don't give you values, set the original to 1. So as you look on the left side, I'm saying that the original torque is going to have to be 1. And for that to happen, force needs to be 1, and for the distance to also be 1. So that's how I'm setting my original up. Now, the question said, what happens if you keep the moment arm the same value, but increase the force? They didn't say how much you increase it. So you could increase it by however much you want. This is not an exact answer that you need. For the sake of it, I just did 3. I could have done 2, I could have done 10. But regardless, when I made a change to the force, it showed me that the torque was now increased. So that's your answer. Basically, the torque increased. All right, so on the next one, there's going to be quite a few different questions. Some of them are like this, some of them are calculations. So I'm going to go ahead and give you guys a few minutes to do these problems. And one of them is a little bit trickier. So take your time, and we will touch base in about a couple of minutes. All right, so that should have been enough time for you guys to have at least solved some of these. Hopefully, get through all of them. But quite a few of these are very quick. The one that might have taken you a little bit longer is number 5, and we're going to discuss that one in detail. But let's go ahead and let's go over some of these. So, number 1, what happens to torque if your force remains the same, but you decrease the distance? Well, they're directly proportionate, so that's going to be the torque decreases. Number 2, if you apply a force of 15 newtons on a door at 0.75 meters away from the hinges, what's the torque? So your F is your 15 and your R is 0.75 meters. So you multiply 15 times 0.75 and you get your torque as 11.25 Nm. Number 3, another concept question. What happens to torque if the distance of your lever or moment arm remains the same, but you decrease the force? So the R remains the same value, but you lower the F. In that case, the torque also decreases. And number 4, this one is going to be one where they give you, again, hypothetical question, but it's for you to use. It's kind of the exact numbers what they change to. So what happens to torque if the force is 4 times greater and the distance is half? So if we go to our original versus new method, like we should have been with number 1 and 3, the original, we're going to say that it's always 1. And then in the new method, it's going to say that the force is now 4 times greater. So our F would be 4, but the distance is half. And if the distance was originally 1, half of that is 0.5. So 4 times 0.5 would be 2. So the torque is 2 times greater, or if you could say it as 2 tau, twice the original torque. All right, let's go ahead and look at number 5. So if you got to this one, you may have just been in the habit of just simply setting it up. You may have kind of missed something, but the question says if you hold a 5 kg ball in your hand, which is 30 centimeters away from your elbow, what is the torque on your forearm, assuming that the forearm is weightless and the pivot is at the elbow? So the 5 kg isn't your force, that's a mass. And you should also remember that any kind of distance should be in meters. You might be looking at it and be like, well, I can't be, solving for this if I don't have the force, but that's not true, because remember what force is? Force is mass times acceleration. So with number 5, we're going to be looking for torque, or tau. Our mass is 5 kg. The lever arm distance should have been converted from 30 centimeters to make it 0.3 meters. And the equation that we want to use is torque is equal to force times R. Now, obviously we don't have force, but that doesn't mean that we can't solve for it, because force is F equals ma, and the A is your acceleration due to gravity. So that F can be replaced with simply m times A. And again, it's always your responsibility to remember the acceleration due to gravity on planet Earth, and that's 9.8. So we get 5 times 9.8 times 0.3. So the torque here is 14.7 n times m. So this is, obviously a good example, because 1, it showed you that you got a mass, and it shows you that how you can go ahead from force into mass times acceleration. But 2 stresses the importance of always remembering to convert from centimeters to meters, or from any other kind of unit of meters into meters. So whether it's kilometers, millimeters, whatever, our distances should be in meters. Okay, so now let's go ahead and look at a different sample problem. 2 children are sitting on a seesaw as shown in the picture. The seesaw is supported directly in the middle by a fulcrum. That's the point where it rotates from. And how far from the fulcrum should the 45 kg child sit in order to balance the seesaw? So the problem itself is not giving us the numbers. This is us having to look at the picture. We have a 30 kg child on the left who is 3 meters away from the fulcrum. So the 30 kg child is 3 meters away from the fulcrum. and the 45 kg child is sitting somewhere that is causing this to be balanced. But we just want to find out the exact distance from the 45 kg child to the fulcrum, which is the R for that individual. So here are some key things that you need to be aware of and some key terminology that we're going to visit again. Okay, for the seesaw to be balanced, it means that the net torque should be 0, right? So the torque of the child on the left balances out the torque on the child on the right, and it's 0. So the net torque needs to be 0. When that value is 0, that's set to be balanced. And this is known as static equilibrium. So a condition where objects are not rotating. So those are all key terminology. Just be aware when you have a seesaw or something where objects are balanced and they're not rotating, that net torque is 0. The torque on the left-hand side is canceling out the torque on the right-hand side, meaning that they're both equal to each other. They might just have different forces and different lengths, which is what we saw in that problem. So in a nutshell, the 45 kg child's torque must be equal and opposite to the 35 kg child's torque. And the epsilon means net, and remember that net means sum. And when you do sum, it's basically all your positives and negatives added together. So in this case, we're talking about net torque, and it's all the positive and negative torques. And remember the counterclockwise versus the clockwise. So this is our image again, and for the 30 kg child, if it was to go down in his direction, that would be considered counterclockwise. For the 45 kg child, if his or her mass was to go downwards, that would be considered clockwise. So based on that, we can go ahead and decide which one's a positive and which one's a negative. So the 30 kg child on the left causes a clockwise twist, which gives us a positive torque. Remember that counterclockwise, it's as if you're going back in time, like in a video game, and that's how you pick up time, so that's positive. The 45 kg child on the right, that will cause a clockwise twist, and just like real life, if the clock is ticking, you're constantly losing it, which means it's negative. So the torque, obviously the net torque is 0, but we have to figure out the torque of each one. So the kid on the right is has a negative torque, and the child on the left has a positive torque. Now you see the 30 and the 45, those are subscripts, and for identification purposes, this can get a lot confusing for some students as we'll solve through it. If it helps you out, just label them as A and B. You might be thinking, why not label it as left and right or L and R? Well, the equation also uses variable R, so you don't want to confuse yourself. But just be aware that if you come across a problem and you see a little subscripts are never used in equations. They're always for identification purposes only. So use whatever method that works. Just be aware that in some problems you may actually see numbers as identification purposes. In this case, we're talking about the torque of the 30 kg child plus the negative torque of the 45 kg child is equal to 0 because that seesaw was balanced. All right, so let's do our knowns and unknowns. We are solving obviously for the R of the 45 kg child. That's the distance that we need to solve for, that's in meters. We have the mass of that child on the right, and that was 45 kg. Now, as we saw earlier in the previous example, mass alone can't be used. We need to have force. So we have to go mass times Ag in order to have our force for that child. So the force for the child on the right is 441 newtons. The R of the 30 kg child is 3 meters. That was the child's distance from the fulcrum on the left. The mass of the child on the left is also 30 kg. And again, mass times acceleration due to gravity will give us our actual force. So the force that is being applied on the left-hand side is 294 newtons. So we can already kind of see that we've got 441 newtons on the right and 294 newtons on the left. So if we want to balance these out, you can kind of think about it as if our equation is t is equal to fr, and if our t needs to be the same exact value for both of these, if the child on the left is having less force and they have a certain number for their distance, which in this case is 3, and the child on the right has greater force but still has to match the same amount of value, that means that the distance should be less. So that's a little quick check before you even start. If you've got more force, you need less distance to achieve the same torque. If you've got less force, you need more distance to achieve the same torque. So use these two advantages when selecting answer choices. At the end of the day, the net torque needs to be 0, and that's where we're going to go from. All right, so let's go ahead and look at this problem. I know it looks a little confusing, but everything's broken down step by step. So we know the net torque needs to be 0. And we said that that is the torque of the 30 kg child plus the negative torque of the 45 kg child is equal to 0. So that net torque is broken down in the second step to those two. And when we take that torque of the child on the left with 30 kg, the equation for torque obviously is force times R. So now we have the force of the 30 kg child times the R, his distance for that individual, minus, because, positive and a negative gives you a minus or a negative. So now it's changed to minus, and we've got a force of the child on the right and their distance, which is what we're solving for. We're going to go ahead now. I already did this for you guys on the previous slide, but if you hadn't, then you would have to remember to go do mass times acceleration of gravity, or just simply mass times gravity. So the mass was 30, the gravity is 9.8, and the distance for the child from the fulcrum from the left was 3 meters. So we get all those replaced, 30 for the mass, the 9.8 for the gravity, and the R is replaced by 3. So that takes care of the 30 kg child's torque. Then it's going to be minus. The reason for that is because, remember, it was originally, it's the sum, but we just added a negative. So it's plus times a negative in that second step that gives us that minus. So we're going to go ahead and substitute our values for that child. His mass was 45. Notice that those highlighted subscripts are no longer there because we no longer need to identify anymore. So 45 was the mass, gravity is 9.8, and R was what we were solving for this whole time. And all of that is still equal to 0. So punch those in your calculator. On the left-hand side, it becomes 882, and that is minus 441 times R. So it's equal to 0. Well, we want to go ahead and solve for R, so we need to, get one of those on either side. And in this case, you can do whatever you like. You could either subtract 882 and just divide by negative 441, or you could add 441R on both sides, which is what we did here. And you get 441R is equal to 882. Since you're still solving for R, divide by 441 on both sides. 882 divided by 441 gives us the R for the child on the right as 2 meters. So the 45 kg child must sit 2 meters away from the fulcrum in order for the seesaw to not rotate and to be balanced. So when you look at the picture, and I'm going to go back to the picture in a second, as we saw, or as we've discussed, if you need to have the same amount of force, if you need to have the same amount of torque between two objects, two different forces, if you have a greater force, like we do with the child on the right, you need less distance. If you have less force, like we do on the child on the left, you need a greater distance. So that answer of 2 logically makes sense because it's less than 3. All right, so here is the full example and the steps. This would be about the most complicated type of problem you'll ever come across. You just have to make sure that you take the proper steps and know the difference between, net torque and when it's balanced, what that means, static equilibrium, and so on. Again, just follow along, identify when you need to. If it helps, use A and B instead of their numbers, because I have seen students go, 30 times 9.8, and then they see that little 30 again, and they multiply by 30 again. That is not something you want to do. So those 30 and 45 that are highlighted was just for identification purposes, and subscripts never get used in our actual equations. Okay, so that is it for today. Hopefully this was helpful. Have a wonderful day, guys.